Okay, class, the recording is started, so we continue from where we left off. You can see my screen, I hope. Now, this is a proper example of how to use POSIX-compatible system calls in order to read from and write to files. The objective is to read all of the contents of the source file and write it into the destination file. A very simple task. Now, let's see what is the proper way of doing this. Now, of course, always you are supposed to have you are supposed to control, of course, if you have the proper number of command line arguments, if they are in the proper format. And of course, if they are not in the proper format, you should always have a function for printing on screen how to use your program. So what is the number of expected parameters? What is the format of those parameters? Are they strings, numbers, and so on? Now, here we check the input number of parameters. If they are not correct, we print on screen the usage. And of course, we use fprintf in order to print to the standard error device, not to standard output. Then we use the open system call with the proper read flags to read from the, in order to read the contents of the source file. And of course, we will then write to the destination file. Now this will happen in the copy file function. All we do is, in the main function, we open the source and destination files and give those file descriptors to the copy file function. Now, what are the read flags and write flags? The read flag is, of course, read only. We are only supposed to read from the source file, so we do not use unnecessary permissions. Only that much, only the one that we need. The write flags, of course, are or create or exclusive or write only, so we are opening it in write only mode. We want to create the destination file, and if it doesn't exist, and if it does exist, we want it to return an error. So we combine these three flags. I hope you are clear on the use of the O exclusive flag. It is important. And what are the permissions of the destination flag? Sorry, of the destination file? It's read and write for the owner of the file. Okay, so we open both the source and destination files using the open system call, and then we invoke the copy file function, which returns the number of bytes that have been copied successfully from source to destination. And how does the copy file function work? Now, this is where the magic happens. Now, pay attention to this file, to this function. Now, we have a buffer size of 1 kilobyte, represented by bulk size. We have internally in the copy file function a buffer of that size. We have the BP pointer, 2 integers to hold the number of bytes that have been read and number of bytes that have been written, and of course the total number of bytes that have been transferred. Now we have an infinite for loop, and what's happening in this for loop? Now pay attention to this while. In the while loop, which has no body, the while loop has no body, ana gövdesi yok while döngüsünün. What does it do? It reads bulk size, at most bulk size bytes from the source file into the buffer. And when does the condition inside the while loop gets true? If it returns -1, which means if it encounters an error during reading and logical end, and that error is intra. So if the read system call encounters an error and that error is signal interruption, what does it do? The while loop repeats. So it is telling it to read again. Why? Because we were interrupted. So when is it going to exit this while loop? It is going to exit it in 2 cases. Either if it reads successfully something, or 0 if it reaches the end of the file. So if it doesn't return -1, so a successful read, or if it returns an error, but it is not due to an interruption by a signal. So something else has happened. Now, if something else has happened, so if there is an error, but it is not a single interruption, so something else, something more serious has happened, we control the number of bytes read. If it is negative or 0, that means either an error has taken place other than signal interruption, or we have reached the end of the file, so it has returned 0. In which case, we break out of the for loop. Nothing left to do. Now, if this hasn't happened, So if it has returned a positive, strictly positive number of bytes read, so at least one byte has been read, what do? Well, in that case, we are going to write it to the destination file. So as long as we have bytes read greater than 0, we have a while loop inside it, which does the same thing as the previous while loop. It keeps on repeating the writing attempt as long as it gets interrupted by a signal. If we get interrupted by a signal, it tries to write it again and again, up until it is successful. In which case, it will get out of the second while loop, because either it has successfully written something, or an error has taken place other than a signal interruption. If an error has taken place other than signal interruption, bytes written less than 0, we break out of the while loop, so we cannot do anything more. There is a serious error going on. Otherwise, we update the total number of bytes that have been written. We remove the number of bytes written from bytes read. So maybe we have read 500 bytes, but we have written only 12 of them. So we will continue writing those bytes up until no bytes read have been left. And of course, we are updating the offset of the buffer where we are going to read from the source file. So we are updating BP. And eventually, of course, we are checking whether, if we get outside of the while loop, whether the bytes written are negative or not, in order to know if we have exited because we have finished our task or because an error has taken place. If an error has taken place, we exit the for loop. But if we have simply finished up the bytes that we have to write, in that case, bytes written will be 0, and it will continue the for loop. And eventually, of course, it returns the total number of bytes that have been transferred from source to destination files. What I want you to remember from this function is this while loop right here, the one that it uses for reading and the one that it uses for writing. This is how you're supposed to do things. Not only you are checking whether an error has taken place or not, but you are trying to fix it by repeating those calls as long as they are interrupted by signals. Any questions about this function? This brings us to our next system call, lseek. Now, when you open a file for reading or for writing, by default, the offset will be at the beginning of the file, imlech, the cursor. Now, you can move that cursor inside that file. You can move it wherever you want to in that file. And for that purpose, you can use the lseek system call. It receives 3 parameters: the file descriptor of the open file where we are going to move the cursor, the offset, how many bytes we are going to move it, and of course, the reference, whence, where from those bytes are going to be counted. Now, depending on the value of whence, which is a constant that can take 3 values, seek set, seek cur, seek end, the meaning of the offset changes. So if whence is, so if the third parameter is set to seek set, that means the offset is going to represent the number of bytes from the start of the file. So if it is 10, it will go to the 11th byte, and so on. If the third parameter is seek cur, that means offset represents the number of bytes from the current position, and it can be either positive or negative, so we can go upwards or downwards. And if whence is seek end, in that case it represents the end of the file. In which case, again, however, the offset can be positive or negative, so we can move the cursor beyond the end of the file, which will only make the file larger. And what does it return? It returns the new position with respect to the beginning. You can use it with any file except for sockets. Example. Here, for instance, we call lseek with the file descriptor fd. So 0 seek set, it will put the cursor to the beginning of the file. 0 seek end to the byte right after the end of the file. -1 seek end to the last byte of the file. -10 seek cur, 10 bytes before the current location. and 10,000 seek and 10,001 bytes past the last byte of the file. These are common uses. Here, for instance, what do we do in this example? In this example, what do? We create, we are going to create a 1 GB file. So we have a constant int megabyte representing, is the 1 GB file? No, it's a 1 MB file. So we have a constant representing a 1 MB length. The file name has been provided as a command line argument. So we use, so we convert this megabyte into a size t type length variable. We multiply the megabyte with the integer that has been provided as a second command line argument. So if we call it with, I don't know, 1024, that means we are going to create a file of exactly size of 1 GB. We open the file with the write only or create or exclusive flags and with the mode 666. And what does this mode mean? It means we are going to give read and write permission to the user, to the group, and to the others. Then we have some magic. We call lseek and we tell it to use the seek set reference, which means from the beginning of the file, and we are telling it to go where? Length -1. How much is length? Well, let's say that argv2 is 1024, so we are trying to create a 1 GB file. In that case, it will go to 1 GB, exactly to 1 GB from the start of the file. If we had used exactly length, it would have gone to the byte right after 1 GB. And to that location, we write a single 0 byte using the write system call. And then we close it. Now, what do we expect as a return, as a result of this program? We expect it to create a 1 GB file. So if we here, for instance, we are using the df command in order to check the amount of free space on this drive. We see that HDA5 has a size of 2.9 GB. It's an old drive. And we have an available space of 655 megabytes. Now, if we execute lseek huge big file with 1024, so if we try to create an actual 1 GB large file, we see that the file has been created right here, big file, exactly of size 1 GB. However, if you check the use of disk space, you will see that the available disk space is still 655 megabytes. So even though we have created a 1 GB file, the disk space, the used disk space haven't changed. But if we try to open the file that we have just created, we can actually see that it contains 1 GB worth of zeros. However, it is not accounted for in terms of disk space. Now, this is a property of POSIX systems, and especially of Unix systems, which can actually sense it. It can actually understand that you are creating a sparse file, a file that has very little content, a file that actually just contains 1 0 and nothing else. Because that's what we have written into the file, just a 0 character at the end of it and nothing else. So what it does, what the system does is, it does create the file, but it does not allocate 1 GB worth of space from the hard drive. If you try to write something additional into the drive, then it will start allocating space for it. It doesn't know whether you are going to use that 1 GB or not. Maybe you are going to write only 1 byte per day. So it is only going to allocate enough room, enough space to hold those bytes. So while the file grows actually with content, it is then and only then that the system is actually going to allocate disk space for it. This is something very useful when you have files representing the drives of virtual machines. So let's say that you create a virtual machine with a hard drive of 500 GB. So it is not going to create one huge 500 GB file representing that drive. Instead, it will be a file that exists on the system. It will be noted down that it must have a size of 500 GB, but in reality, it will only occupy space corresponding to the actual contents that it has. This doesn't exist in Windows. In Windows, if you do the same thing, it will actually create a 1 GB file containing nothing but zeros. Any questions? And this brings us to input-output control, IOCTL. Now, this is the Swiss Army knife. İsviçre ordu çakısı. Swiss Army knife of the file input-output system calls in the POSIX world. It is there for non-standard operations. So for anything else besides opening, closing, reading, and writing, you have input-output CTL. For example, you want to eject a CD-ROM, you can do it. You want to access a printer represented by a file and do something special with it. I don't know, change the dimensions of the paper, check whether it has ink or not, or you want to access a scanner and change the mode that it works in from color to black or white, anything. You want to access the GPU, you want to access the Ethernet card, any file, and you want to do something different other than reading, writing, opening, and closing, IOCTL. Now, exactly which commands are supported by IOCTL, that depends on the device. And as you can see from the function signature, it admits what? What is the meaning of these 3 dots? What is the meaning of those 3 dots?
It can be anything, any integer string, I don't know.
The meaning of those 3 dots is that this function can get a variable number of parameters. You can call it with 2 parameters, 3 parameters, 10 parameters, 25 parameters. Optional parameters. Why? Because we never know what kind of a device we are going to manipulate with IOCTL. Maybe it is a device that requires 56 parameters, so IOCTL must support it. Hocam, how will I know with what kind of parameters to call IOCTL when I'm manipulating a new device that just arrived to the office? You will check the documentation. You will read the documentation of that device, and you will see there what kind of parameters it supports using IOCTL. This is the key that we have in order to access the API of an arbitrary device. So it's a special system call. So it is beyond the scope of this lecture.
Sir, can I ask something?
Yes.
Does C have optional parameters?
Does who have optional parameters?
C, language C. Because as I know, it doesn't. And how does it work?
Yaşar, siz bunları 1. 2. sınıfta yapmadınız mı ya? Ciddi misiniz şu anda? Hiç optional parameter kullanan fonksiyon yazmadınız mı 1. sınıfta?
Hocam C'de yani optional bir parametre koyamıyorduk ki, ben öyle hatırlıyorum yani.
Arkadaşlar, bu soruyu duymamazlıktan geleceğim. Böyle bir soru sorulmadı. C'de tabii ki optional parametre var. Tabii ki var. Ben bir şeyle konuşayım ya. C'yi kimden alıyorsunuz? Yakup Hoca'dan mı? 1. sınıfta.
Evet hocam.
Peki. Ben bir onunla konuşayım ya. Ben optional parametreleri yaptığınızı düşünüyorum. Geçmiş yıllarda hep öyleydi. Tabii ki var arkadaşlar. Optional parameters are part of the C language. They have been part of the C language for a very long time.
Hocam bir ödevde vardı sadece hatırladığım kadarıyla.
Güzel, bir defa yetiyor zaten. This brings us to FCNTL. Now, FCNTL is a special system call in order to manipulate flags associated with a file descriptor. It can be used in order to duplicate, kopya yapmak için, in order to duplicate file descriptors. And it can also be used in order to lock and unlock files, which can be useful, not very useful. Bu veriyi kaldıralım buradan. Can be useful for inter-process communication. Now, how does it work? Setting a lock on a file, and what does it mean to set lock on a file. It means that if you have locked that file in a process, another process that tries to access the same file will not be able to access it. But do not be fooled by this. Lütfen burada aldanmayın arkadaşlar. Burada şey yok. Sistem genelinde bir kilit yok. This is not a system-wide lock. So just because I have locked a file in my process, this doesn't mean that some other process, either belonging to me or to some other user, that will try to call open or write or whatever on that file will not be able to do it. This lock is advisory. It is an advisory lock. Şimdi diyeceksiniz ki hocam what is an advisory lock? Geliyoruz arkadaşlar. Sabır. Now first, how does it work? To place a lock on a file, you first create and zero out a struct flock variable. You set the type of that field to read lock or write lock, depending on what kind of a lock you want. And you pass that structure to fcntl, calling the set lock operation. Let's look at an example, and then I will explain the why they are advisory. So here, for instance, we have a struct flock represented by the variable lock. We first open the file, represented by the path name file in the write-only mode. And then we set to 0 using memset the contents of this struct. Memset ne yapıyordu? Belli bir byte ile belli bir alanı dolduruyor. So here, for instance, we are giving it the address of lock. We are giving it the size of that struct, and we are telling it to fill it with zeros using memset. Okay. Memset is a library function. We are setting the type of the lock as write lock. Dolayısıyla bu bir yazma kilidi olacak. This will be a lock against writing. And we call fcntl by giving it the file descriptor of the file that we want to lock, giving it the address of the lock structure, and of course telling it what to do. We are telling it to set a lock. Now the file is locked. Now if we try to do anything with this file right now inside this process or in some other process, there will be problems. What kind of problems? Şu noktaya arkadaşlar dikkatinizi çekmek istiyorum. If right now that the file is locked for writing, if some other process or this process tries to write into that file using the write system call, it will succeed. Şu anda ben yazmaya çalışırsam write'ı kullanarak ister bu süreçte ister başka bir süreçte yazabilirim. Bir engel falan yok. İyi de hocam bu ne biçim kilit diyeceksiniz. Hani o kadar kilit koyduk yazmaya karşı. Kimi durdurdu o zaman bu? What this lock has accomplished is the following. Now if somebody else or this process tries to call fcntl trying to set a lock on it, bir başkası kilitlemeye kalkarsa işte o orada tıkanacak. Daha öteye geçemeyecek. fcntl geri dönmeyecek. If this process or some other process tries to call fcntl trying to lock it, it is that system call that will be blocked. It will not return. Blocktan kastettiğim o. That's what a lock means in this context. That's what I mean when I say POSIX locks are advisory. It doesn't mean that write or read block. It means that fcntl can be used in order to block other fcntl calls. So for this system to work, so let's say that you want to place locks on files in order to make sure that only one process accesses that file at a given time. What do? You make sure that those processes use fcntl to lock the file before accessing it. So they must have agreed beforehand to use fcntl to first lock the file, and if they succeed in locking it, then they continue to manipulate its contents. But if some other process who knows the file name doesn't use fcntl and directly uses open and write in order to open it and write inside it, it will open and write it. There is nobody stopping it. That's what I mean. These locks are advisory. Sadece hani tavsiye niteliğinde şeklinde çalışıyorlar. Hani biz kendi aramızda anlaşıyoruz. Abi senin süreçte fcntl kullansın, önce kilidi alsın, sonra yazsın. Ben de önce kilidi alacağım, sonra yazacağım. Ama aramızda da bir tane akıllı'nın biri çıkıyor. Abi ben FCNTL kullanmayacağım. Doğrudan open yapıp write'la yazacağım içine. Adam yazacak. Bizim kilitler onu durdurmayacak. Olay bu. Any questions about these logs? Long story short, do not really trust them. So you need to be certain that the processes that you're trying to synchronize in terms of access to the files, they have all agreed to use FCNTL before accessing the file. Because if they omit it, if they ignore it, if they forget it, the entire system breaks down. The logs will not work in that case. So it only works if all the processes agree to first get a lock using FCNTL and then manipulate the contents and then set the lock free. And here you can see how you unlock it. So the same, you are using the same struct flock. You set the type to funlock instead of lock as it was before. And then you simply call FCNTL, setting it, telling it to update the lock. That's all there is to it. But as I said, please keep in mind that these locks are advisory. So if you want the system to work, and by system I mean if you have multiple processes that you want to synchronize in terms of access to a file, then you must make sure that all of those processes use FCNTL to first lock the file, then update the file, then unlock it. This brings us to redirection. If you have any questions, feel free to ask whenever you want. Now, what is redirection? Now, normally, under normal conditions, when class, I'm getting a message that I have bad network quality. Can you hear me clearly? Is the sound okay?
It's okay, sir.
Yes, it's okay.
Okay. Teams is acting a bit weird today. Let's see. Now, under normal conditions, a process, of course, reads from the standard input, writes to the standard output. In case of an error, prints that message to standard error. But of course, we are free to redirect them. So just because a process starts with 0 set to standard input, it doesn't mean that it has to continue that way. I can change it in whatever way I want to change it. How? Redirection. Now, you can do this either at the shell level, or you can do it internally using system programming. Now, at the shell, you simply use the redirection operator. So this command, for instance, tells that we want to execute the MyScript script located in the present directory. We want its output, so 1, to go to the file results.log instead of the monitor, instead of the standard output. And we are also telling it to redirect the standard error represented by the file descriptor 2 to where? To the first file descriptor. So whatever is the standard output, we want the standard error to be redirected to the same place as well. And what is the standard output? It is results.log. So basically this command means redirect both the standard output and the standard error to results.log. Or another example, we are telling it to execute the MyScript script located in the present directory. We are telling it to redirect standard error to wherever the standard output is. And we are telling it to get the output of this command and give it as input to the command less. Arada bir boru var aslına bakarsanız. Birinin çıktısı diğerinin girdisi oluyor. The output of the left side of the pipe becomes the input of the right side of the pipe. And what is the output of my script? Both standard error and standard output are represented by the same file descriptor. So all the errors and the output of my script become input to the command less. Any questions about the shell level redirection? Okay. Now, how is redirection working behind the scenes? I mean, okay, we can do this on the shell. This is nothing new. I mean, I'm guessing that you know this stuff ever since your first year. But how does it work at the system level? Because we know that files are represented by file descriptors. So what happens when you duplicate a file descriptor? Can you have two file descriptors pointing to the same file? Of course you can. There are many ways of duplicating file descriptors. In fact, there are three different ways. The standard one is to use dup2, duplicate. It receives two parameters, the old file descriptor and the new file descriptor, and it makes a copy, a duplicate of the old file descriptor as the new file descriptor. Amojam, what if new file descriptor already exists? Well, in that case, if new file descriptor is already open, duplicate first closes it. dup2 first closes it. So if you use, for instance, dup2 1.2, that means 1 is redirected. 1 is reopened as 2. So that means 2 is redirected to 1. So 2 is closed in this case, whatever it was pointing to. So 2 was pointing to, I don't know, maybe a log file or whatever. It is closed, and it is now pointing to wherever 1 is pointing to. So it has made basically a copy of 1. So both file descriptors 1 and 2 now point to the same file. Another way of doing the same thing is by using fcntl. So you give it old fd, you give it the flag fdupfd, and of course start fd. So this is the target fd, and it will make a copy of old fd as start fd. Now it will use new fd, or rather start fd, as a new file descriptor. It will use the lowest unused file descriptor that is greater than or equal to start fd. So let's say that you call it with 1 fdupfd 2, but if 2 is already occupied, then it will check 3. If it is already occupied, it will check 4, then 5, then 6. The first file descriptor that is available, it will become a copy of old fd. So fcntl works a bit differently than dup2. Any questions about this duping? Okay. Now, class, before we continue with file implementation, I will take a break for 2 minutes, and then we will continue from the point where we left off. A 2-minute break. Okay, class, we continue with the implementation of files in a POSIX system. Any questions so far? Okay. Now, the fundamental principle in the file system design of POSIX system is that the actual contents of files and the file metadata, so data about data, metadata, they are separated. They are kept separately. The metadata is stored in a structure called an inode, which is short for an index node. The inode contains the size of the file, the location of the file on the drive as an address, who owns the file, the time of creation, time of last access, time of last modification, permissions, and so on. Now, in addition to all of this statistical information, the inode also contains addresses to the blocks of data on the hard drive. Now, this is a structure of fixed size, of fixed length. So if the file is too large, it has an indirection system, so pointers to blocks of pointers. Or if the file is even larger, it has a set of pointers to a block of pointers that points to another block of pointers, and so on. And thanks to that triple indirection, it can represent really huge files. Now, how does all this work exactly? Now, here we see on the left an inode, which is a fixed length structure representing a file. So it contains the permissions of the file, the timestamps, who are the owners of this file, and so on and so on. And of course, it contains, as a fixed length structure, addresses to direct blocks. Now, these blocks, they are located on the hard drive. That's where you keep the actual contents of your files. Now, of course, you have a limited number of direct blocks. If those blocks are not sufficient in order to store your file contents, then you can use the single indirect address, which points to a structure of more data pointers, or you can use the double indirection or even triple indirection. And this allows you to represent really huge files on a given system. Now, how exactly large? Well, for that, you will need to have as input the block size, which can be 1 kilobyte or 4 kilobytes and so on. And of course, you need to have access to the size of the inode in order to calculate exactly the maximum possible size that the file can have under this organization. But the beauty of it, the most important property of this organization, is that it allows us to keep files in non-contiguous, sürekli olmayan areas of the hard drive, in non-contiguous areas of a hard drive. So you can have a file that is 1 gigabyte large, 100 megabytes of it can be at one place in the hard drive, 50 megabytes might be at some other location, another 75 megabytes might be at some other location, and so on. So it can be fragmented, parçalanmış bir şekilde, it can be fragmented all over the hard drive, but it's still a single file. Now, okay for files, but what about directories? Now, directories are very, very efficient. A directory in a POSIX system, and especially in a Unix system, only contains pairs, shift pairs of inode numbers and file names. Dikkatinizi çekerim arkadaşlar. Pay attention that the inode does not contain the file name. It contains a lot of things, but it doesn't contain the name of the file. The file name is contained inside the directory. So for instance, which directories do I have right here? I have the bin directory. So if I open the bin directory, I see that it contains only the names. It is not showing me the inodes because the VI program only works that way, but the directory only contains the names of the files and subdirectories that it contains, and of course their inodes. Hocam nerede bu inodes'lar? For instance, if I use lsil, it prints the inode numbers corresponding to each file as the first column. Here you can see the inodes, and they are unique for each file. as you can see. Now, why do we have it in this way? Now, the advantage of this system is that if you try to change the name of a file, it's very easy. You just go to the directory, which contains pairs of inodes and file names, and you just modify a string. That's it. Changing a file name is extremely efficient. What about copies? Now, you only need to have one physical copy on the disk, but it can have multiple names for it in different directories. So you can have two directories containing the same different file names, sorry, but they are associated with the same inode. So you can have the same inode associated with multiple file names. But remember, there is a one-to-one correspondence between the inode and the actual file contents, but there is a one-to-many correspondence between file names and inodes. 3, directory entries are of variable length because the file name is of variable length. Directory entries are small since most of the information about each file is kept in its inode. Manipulating small variable length structures can be, of course, done efficiently. Now, larger inode structures are fixed length. Now, inodes have a fixed length. That's the key issue. So what do you remember from this? Inodes have a fixed length. There is a one-to-one correspondence between inodes and file contents. The file contents can be fragmented all over the hard drive, so files are not stored contiguously. And 3, directories are nothing but files containing pairs of inodes and file names. Nothing more. That's it. Any questions about this part? Now, then what about links? Now, there are links in the POSIX system, and there are two types of links: hard links and soft links, or symbolic links. Now, what is a link? A link is very simply an association between a file name and an inode. A symbolic link, on the other hand, is an actual file that stores the path name of another file. So you can have multiple file names pointing to the same inode, associated with the same inode. If you have multiple file names associated with the same inode, those are called multiple hard links. You can use the ln command to create additional hard links, or the system call corresponding to the same command. So old path and new path. So the new name and old path. So the target and the name of the link. And you can use unlink in order to remove those links. Now, as long as there is at least one link to a file, that file continues to exist on the system. If you remove even the last link from the file system, then the file is deleted. Creating a new link to a file doesn't take any additional space, just one more directory entry. Example, we will get back to the symbolic link. Here, for instance, we create a file named file1 containing the string cat. Then we create a file named file2 containing the string dog. If we ls them, we can see that we have two files, each with its own inode number. Okay, so two distinct files, two distinct inodes. Then we use the ln command to create a new link called link to file1. Okay, and if we list them again, we will see that we have file1 and we also have link. They both have the same size. They both have the same inode, which means they are both pointing to the same file. And here we can see the total number of links to that file, which is 2. And we can use, of course, unlink in order to remove those links. Removing a link doesn't mean that you remove the file. You just remove the directory entry. The file is removed only when you remove the last link. Then it is removed. What about symbolic links or soft links? A symbolic link is an actual new file, but it only contains, the only contents of that new file is basically the path to the target file. Here, for instance, we create a symbolic link called slink to the source file2 using ln-s. So we have file2, the original file, containing 4 bytes with its own inode number. And then we'll create slink, which points to file2, but it has its own inode number. So an slink is an actually separate, distinct file. Whereas with hard links, you only create links, directory entries pointing to the same inode. Temporary files. Now, temporary files are, of course, often needed by programs in order to store temporary data. And of course, we always keep them in the /tmp directory. Why? Because we know that when the system reboots, all the contents of the /tmp directory is going to be deleted. That's the place to store temporary files. How do you create temporary files? What is the proper way of doing it? The proper way of creating temporary files is to use the mkstemp system call. You give it a template for the name and path of the temporary file, and it will create it. It will return the file descriptor so that you can use it for reading and writing, or -1 on error. Example, here we have the template, so /tmp/ something something xxxx uppercase. And if you call mkstemp with that template, it will replace the uppercase X part with some random content in order to make sure that it is unique. Then it is returned as an open file. You can write to it, you can read from it, you can do whatever you want with it. And once you are done with it, you unlink it, which means that it is going to disappear from the system since you have no other links, but not until you close it. When you unlink it, it gets removed if that is the last link that is removed, but it will actually get removed only after closing it. So after unlinking, the file is still there. It disappears from the file system, but it is still accessible by this process. Until when? Until you close it. After you close it, then it is gone permanently. Any questions about temporary files? And this brings us to the topic of file stats. How do you access the meta information of a file? How do you access who owns the file? How do you access the permissions of a file? How do you access the time of last modification? How do you access the time of last change? And so on and so on. There are 3 system calls that we can use in order to access the properties of files, its size, and so on. And those system calls are stat, lstat, and fstat. Now, the difference between stat and lstat, they have the same parameters, but the difference is that if you give a symbolic link to stat, it will return the information of the file pointed to by the link, whereas lstat will return you the information of the link file itself. Remember, symbolic links are separate files. So stat returns the information of the file pointed to by the link, whereas lstat returns the information of the symbolic link file itself. Fstat behaves in the same way as stat, but it receives an open file descriptor instead of file name. What are the available stats that we can access? We can access the identity of the device where the file is located. We can access the inode number, the file type, the permissions, the number of hard links, who is the owner, who is the group owner, the total file size, the number of blocks allocated, the time of last file access, file modification, last status change. By status change, we mean change of permissions, not change of contents. Change of contents is the modification time. So be careful with these different things. So how do you access these? Now, if you try to access them directly, it is a bit impractical because you have to do some ending and ORing and masking and so on. That's why we have macros in order to achieve this. Now, normally, it returns a large number, which basically the ST mode number, and you can use the different bit fields in order to figure out what it contains by ending it with certain masks. Now, instead of doing this, instead of taking statbuf's ST mode, ending it with IFMT, and checking it if it is a certain constant or not, instead we use macros. Which macros? Here, these, for instance. You can use the isreg macro and give it the stmode field of the statboof structure in order to check whether it is a regular file. You can use isdir to check whether it is a directory. You can use isFIFO to check whether it is a FIFO, and so on. So in order to figure out the type of the file. Oh, sorry. I went to the beginning. Here we have an example. So we receive one command line argument, the path of the file of which the stats we are going to study. We have a struct stat which will contain the statistics of that file. We call stat, we check whether it is successful, and then we print on screen. What do we print? We print the name of the file, and underneath it we print the size of the file. We print the number of links to that file. We print the inode number of that file, and then the permissions. Here, for instance, we benefit from the macros. We check if it is a directory, isdir. If it is a directory, we print a D, otherwise a dash for a regular file. And then we check by ending with the constants read user, write user, and execute user. We check the permissions, and we print the corresponding character. And we can do the same thing similarly for the groups and the others. And of course, you can check whether it is a symbolic link or not. And when you execute it, it prints out beautifully the output, just like the ls command. So you can use basically stat, fstat, and lstat to write your own ls command. This used to be a homework in the past years. A common question by the students. Hocam, şu alttaki sayı nedir ya? The output that you get at the first row after ls is the total number of blocks occupied by that directory. And if you look at the output of ls, you can see at the first column the type of the file, at the second column the access permissions, then the number of links, the owner, the group, the size in terms of bytes, the modification, the date of and time of last modification, and of course the name of the file as an output of ls. Now, do you have any questions in the meantime? Okay, class. Now, finally, our last two topics for today. Let's take a look at the relationship between open files and processes. Now, class, each process can open up to 1024 files. That's a maximum of 1024 file descriptors per process. Each of them a non-negative integer. For every process, they start from 0. Now, the kernel, in order to maintain, in order to organize this chaos, so which process has opened which file, where is the offset, imleci nerede, neresini okuyor falan filan, in order to keep track of which process has opened what and at which offset it is located, it keeps 3 data structures. First, it keeps a descriptor table, an FD, file descriptor table, for every process. So for every process, it keeps track which file descriptors have been opened by that process. It keeps another system-wide table, so one for the entire system, of all the open file descriptors containing the inode of the file that is open, and of course the offset. İmleç nerede dosyanın içerisinde? Signal settings, etc., etc. This is a system-wide table of all the open files. And of course, it needs another table which makes the association between the open file descriptors and of course the system inodes. So the file type, the owner, the location, etc. Here, for instance, we have such a representation. On the left, we can see that for each process, we have a file descriptor table. So just a table containing the file descriptor number, so 0, 1, 2, all the way to all the way to 1024, and the corresponding pointer. The pointer points to a row in the system-wide file table. So, and that table contains the offset, the status flag, and the inode of that file. And using that inode number, we can actually reach the inode table where we will see whether the file is locked the file type, and more information that is in fact dedicated to the kernel. Now here we can see, however, multiple arrows pointing to the same rows. Example, process A has two file descriptors referring to the same file descriptor 23, right here. Both 1 and 20 point to row 23. File descriptors 1 and 20 point to row 23, to the same row. How can this happen? Well, for example, it can happen when process A has duplicated the file descriptor. It made a clone of file descriptor 1 as 20, and so now both of them point to the same location, and of course both of them use the same offset. So if one of them writes something, the offset will also move for the other one too. We also have processes A and B, two distinct processes, where there are two file descriptors referring to the same file. Here, for instance, file descriptor number 2 of process A points to row 73, and file descriptor number 2 of process B also points to row 73, which means both of these file descriptors point to the same file in the system-wide open file table, and they have both the same cursor, the same offset. So if one of them writes something, the cursor will move for both of them. Now, how can this happen? Two distinct processes with two open files at different file descriptors, same file descriptors pointing to the same file. Well, it can happen, for instance, if A and B have a parent-child relationship. So if, for instance, process B was created by process A, in which case process B has inherited all the open files of its parent. Yani miras kaldı B'ye A'nın bütün açık dosyaları. So it has the same file descriptors pointing to the same file. And we also have process A and process B with the same file descriptor, with different file descriptors, 0 and 3, pointing at distinct offsets, which, however, point to the same file. Let's look at it. Here we can see file descriptor 0 in process A, which points to row 0. And we can also see file descriptor 3 in process B, which points to row 86. So two different rows in the open file table, the system-wide open file table, but both of them point to the inode 1976. Now, how can this happen? Well, it can happen very simply when, for instance, two processes open the same file. My process opens this file and your process opens the same file, which means we have opened them independently, which means you have your own offset, I have my own offset. But however, we are both manipulating the same file. So they both point actually to the same file with the inode number 1976. Any questions about this stuff? And this brings us to our last topic for today, buffering. Now, class, obviously, the slowest component on a computer is the mechanical one. Now, a CPU is an electronic device. Memory is electronic. These are just electronic circuits. So they are extremely fast. A CPU is, of course, way faster than all of them. And mechanical devices, such as hard drives, are, of course, way slower. Now, there have been some advances thanks to solid drives, solid-state drives, SSDs, but still, they are not as fast as the CPU or main memory, which means there is a speed difference between these devices. And as a result, when you have a CPU which executes billions of commands per second in theory, so if you have a 3 gigahertz CPU, that means you can execute in theory 3 billion instructions per second. Now, if you execute these instructions so fast, and some of the processes attempt to manipulate files using those instructions, and the files live on the hard drive or solid-state drive, that means the CPU will very often have to wait for those operations to be completed. So accessing files, writing to files, reading from files, since those files are located on a very, very slow device with respect to the CPU and main memory, that means it is a source of efficiency problems. So for example, if you very frequently call, read, and write on files that reside on the hard drive or a solid state drive, and each of these corresponds to a system call, and each of these only manipulates just a few bytes, well, of course, that system is going to suffer in terms of performance. Now, there are many ways that the kernel handles the situation. Now, first of all, the kernel, without even letting us know, it does whatever it can in order to minimize the number of disk accesses. So even if you make 1,000 different system calls, each of them manipulating just 1 byte inside a file for reading or writing, and especially for writing, the kernel will accumulate them. Çekirdek onları biriktirecek arkadaşlar. It will accumulate them in order to have the minimum number of disk accesses possible. I mean, you will still lose time while executing those system calls, because remember, a system call is an expensive operation, but at least the kernel will optimize to the best of its ability the number of disk accesses by keeping a kernel buffer. So if you, for example, if you try to simply transfer 3 bytes of data from memory to a file, because the number of bytes is very small and it is not worth a disk operation, the kernel will simply put them in a buffer in the kernel space. And if you try to read them by another process in the meantime, thinking that they are already at the file, whereas they are not, the kernel will still read them from the buffer and return them to you. And your process will be under the illusion that it has read those bytes from the actual file. So the kernel keeps an internal buffer in order to minimize the number of disk accesses. Okay, but is it sufficient? No, it's not. For example, the kernel will perform the same number of disk accesses regardless of whether you perform 1,000 writes of a single byte or just a single write of 1,000 bytes. But of course, the second one is much more preferable. Look at this table. Here, for instance, we are trying to duplicate a file which has 100 million bytes, so approximately 100 megabytes. Now, the difference between these rows is that we are using a buffer size at the first row of size 1 byte and at the last row of size 64 kilobytes. Now, as you can see, the total time that is elapsed, of course, is way greater when you use a buffer size that is very small. Now, this buffer is not a kernel buffer. It is a user buffer. Now, the kernel is still optimizing the number of disk accesses. You cannot control that, really. The kernel is still optimizing the number of disk accesses so that you will not make 100 million disk accesses while using a buffer of size 1. However, using a buffer of 1 at the user space is still way slower than a buffer of 64 kilobytes because we are losing time not due to disk accesses, we are losing time because of the huge number of system calls. So the reason that we have 99 seconds passing in system CPU right here at the end of the first row under the system CPU column is due to the huge number of system calls, not due to the time lost at disk accesses. The kernel is taking care of that part. The kernel is optimizing the number of disk accesses, but it cannot optimize the number of system calls. We are choosing how many system calls we are going to make. And each system call means kernel trapping, transferring of parameters from user space to kernel space, and so on and so on. The stuff that we saw during our first week. So it is always a better idea to use buffering when reading and writing. Now, how can you use buffering? You can benefit. Now, how can you use it? Because we didn't see any buffering with open and write system calls. Now the buffering part is provided by the library functions, the C standard library functions. So fprintf, fscanf, fgets, fputs, fputc, fgetc, and so on and so on. Never use fgets. Fgets bu listede yok. Dikkatinizi çekerim. Don't use fgets. Sorry, don't use gets. You can use fgets. It is here, but never use gets. It is not safe. So the standard library helps us with the buffering so that we will not have to implement it for the read and write system calls. They take care of the buffering part on our name. Now these high level, relatively speaking, high level functions, so fprintf, fread, fwrite, and so on, they do not manipulate file descriptors, but instead they manipulate file pointers. The file pointers are just structs that contain a lot of valuable information. So the current position in the file pointer, pointer to the base of the file, flags, etc., etc., used by the standard C library. Now, how does it work? Now, the buffering is happening internally in the C library. What do we have to manipulate? We can manipulate the form of the buffering by using the setVbuff library function. The setVbuff library function can set the type of buffering. Now, we can set the type of buffering for this stream at the first parameter. Here we have the buffer structure, the size of the buffer at the last parameter, and the mode. Now, the mode can take three values. It can either be stream, boof, or size. Now, if we are using this constant, for the mode, it means no buffering. So the C library function is using no buffering whatsoever. So whatever you send, whatever you give to fprintf, fwrite, fread, and so on, there is no buffering. It is immediately converted to a system call, and the request is made to the kernel. This is by default the behavior when you try to write to the standard error. No buffering. Whatever you send as an error, it is immediately printed. It is not accumulated. But at the kernel side, of course, the kernel buffer still exists. The other mode for buffering is line buffering, LBF. So it will buffer it until a new line appears or if the buffer fills. And of course, there is full buffering. It will first fill the buffer and then send it for reading or writing. Here we have an example. For instance, a buffer size of 1 kilobyte. Here it's the buffer itself. So I am using it for the standard output, and I'm setting it to full buffering for the standard output. So whenever I call printf and so on to print something to the standard output, it will first be accumulated until 1 kilobyte and then printed, as an example. Now, whenever you want to hurry up and not wait for the buffer to fill, and you want to immediately send it to the kernel, you can use fflush. Bu arkadaşlar klozeti çekmek gibi. So you flush the stream and everything goes to the kernel. Here we have a nice representation. So the user data. So we have two buffers as a result. We have the buffer on the user side manipulated by the C library functions. So the standard input output buffer on the top. And we have the kernel buffer at the kernel side. Now the kernel buffer, that is up to the kernel. We have nothing to do with it. The buffer on the user side, we can manipulate it. We can set its type by using setVbuff, the one that we just saw. If we want the buffer to immediately be flushed, we can use fflush. If, for any reason, you do not want any buffering on the kernel side either, and you want immediately anything that you read or write to be immediately sent to the hard drive or the solid state drive, you can also use the osync flag while opening a file. However, this still does not guarantee that whatever you read and write will go immediately to the drive, because it can go to the temporary memory of the hard drive controller and so on. But this is the best that the kernel can guarantee. So it is telling you that if you do not want any buffering whatsoever, so you want really real-time as fast access as possible, and you want to take care of your own buffering, and you do not want to benefit from the buffering services of the kernel or the C library function, then you set the buffering mode in the C library to no buffering using set vbuf. You open the file using the osync flag, and then there will be no buffering whatsoever. But still, it does not guarantee that it will go to the device immediately, since it can still be stuck on the temporary memory of the hard drive controller. But there isn't anything else that the kernel can provide in order to make it any faster. But be very careful if you use no buffering, especially on the kernel side, by using the osync flag, because that means the kernel is no longer helping you in any way. So if you make multiple reads or writes for a single byte, you are going to lose a lot of time. You will have multiple disk accesses, and the system will become, your program will become extremely slow. So it is your responsibility to arrange things, to organize things in that case. Any questions about buffering? Okay, class. So this is the end of the lecture for today. You will have a homework. It will be ready tonight. The details will be in that homework. Yeah. If you have any questions about the homework, you can write them into the Teams channel. I will give you permissions. Yeah, that's all from me for today. Anything you want to say? Any questions?